ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you for tuning in. What we're going to do today is we're going to take a look at half-life. Now, half-life can be applied when we're in kinetics to either zero order, first order, or second order. But for our first year introductory chemistry classes in college, we only deal with half-lives in regards to first order kinetics. And so we're primarily today going to talk about what half-life is and how it applies to first order reactants, okay? So just to frame that, because again, I want you to understand half-life in terms of AP chemistry, we're only going to be dealing with first order reactants, okay? All right, so half-life, the definition, it's defined as the time required for half of the reactants to disappear, all right? And so half-life is exactly what it sounds like. It's defined as the time required for half of the reactants to disappear. So what would that look like on a graph? Well, what we would do is we would have our concentration line, right? If this was my concentration of A and this was, I'm going to go ahead and on this one, I'm going to put number of, actually, you know, I'm not going to put number of half-lives. I'm going to put time, just like if we would see it on any other normal time versus concentration integrated rate law graph, okay? All right, so immediately I see this is not zero order, right? Because if it was concentration versus time for zero order, I would expect a straight line. And so I'm going to go ahead and put up here concentration of A at my naught time. So my beginning concentration or initial concentration of A. So then we go down and we're going to do 1/2 of A naught. Right, and so this would represent my first half-life, and I'm going to go ahead and draw a line, just like basic graphical analysis that you learned in like 8th grade or 7th grade, whenever it was. All right, and then we're going to go again, and we're going to cut it in half. So a half of a half is a quarter of A naught. Right, and again, notice this is all referencing back to the initial concentration still. And then I'm going to go ahead and just for shoots and grins, put 1/8 of A naught. And so what we're going to do is we're going to show on this graph, and it's going to be approximate because I sketched this graph by hand, but what we see here is that the time, and we notate it this way, the time for my half-life is actually constant. All right, and that's one of the properties of a first order half-life, is that the half-life time is actually a constant value. It's concentration independent, if you will. All right, now all the factors that affect rates still apply, all of our descriptions of all that stuff still apply, but the time it takes for half of the reactant concentration to disappear is actually constant for my first order kinetics and first order reactants. All right, and so just to put some values on there, for example, if this was 1.00 molar at beginning, at my first half-life it would be 0.5 molar, and then it would be 0.25 molar, and then it would be 0.125 molar, right? So half-life is not a big deal. Again, it's just the easy, simple concept that we're just doing something, we're cutting it in half. Now, a lot of times what you can do is you can do this and just kind of conceptually do half-life, because you'll just cut it in half and see how many times it takes to get to that concentration, because a lot of times they'll ask you what the half-life is, and they'll give you a time it took, or they'll say, hey, if I go through 5 half-lives, what's the concentration? All right, and so those kind of conceptual problems, you can just qualitatively cut everything in half, if you will, and get to where you need to be. Now, there is a more complicated side to this, and we're actually going to get into our integrated rate law. I'm going to write the integrated rate law on the screen here, which is the natural log of A at some given time, negative rate constant times time, plus the natural log of my initial concentration. All right, and so what we're going to do is we're going to just look at this. I'm going to move some things around really quick. All right, and so I would end up with the natural log of A minus the natural log of A naught equals negative KT. Notice all I did was subtract off natural log of A naught off the right-hand side of that equation. Now, the law, when I have natural logs, when I'm subtracting natural logs, I can actually just combine that. So it becomes the natural log of A over A naught equals negative KT. And so this is an important part, because now what we're going to do is we're going to conceptualize what half-life actually is and just say, all right, if I'm solving this integrated rate law equation for half-life, I would be using 1/2 of A naught. So half of my original concentration. And a beautiful thing happens here, ladies and gentlemen. I need you to see it. Notice that A naught over A naught in this actually cancels out, and so I'm left with the natural log of 1/2 equals negative kT. And this gets into why natural log, or I'm sorry, the half-lives of first order reactions are actually concentration independent, because the way this solves out, it actually cancels out in the process. Now, this particular equation here does represent a very important stopping point in this derivation. It's not the half-life equation that we're going to end with, but it's very, very important. Notice this tells me that 50% of concentration is left, right? Right? How long does it take for half of A naught to be there? And so this is actually a very important, because a lot of the times they'll give you percentages. Now, notice it's not 50%. It would actually be the natural log of 0.5. So I need to make sure that I convert my percentages to decimals here. But this is going to be something that you're going to have to do, all right? That you'll have to see and say, hey, if I'm solving for the time it takes for 50% of the reaction to disappear, or reactant to disappear, this is the type of equation that I'm going to use. I just do natural log of 0.5 equals negative kT. All right? Well, luckily enough, and whatever percentage they give you, if it's 75%, you're using 0.75 there. If it's 83%, you're using 0.83. Whatever it is, if it's first order, you can use that particular equation to solve for the time it takes for a certain percentage of a reactant to still be remaining. All right? And notice, this is that 1/2 represents the amount of reactant, of original reactant, remaining. The amount of original reactant remaining, all right? So please make sure that you clarify that in your mind and get that noted there, because, again, that's a small nuance of how you do the calculation and how the problems that you're going to see are worded, all right? Okay, so luckily enough, the natural log of 0.5 is actually equal negative 0.693 equals negative kT. I'm still solving. I'm trying to get to the half-life equation here. I'm going to go ahead and multiply by negative 1 to get rid of the negatives here, and then I'm going to move K over, and so I end up with 0.693 divided by my rate constant equals the time it takes for half of my reaction to disappear. And this becomes the other important part of this equation. Notice, with a rate constant, I can solve for half-life, or with a half-life, I can solve for a rate constant, and so this is another way that we can actually determine that rate constant, and another way that we can mathematically define that half-life, all right? And this is our other one. These are the two equations that you're going to be responsible for out of this particular lecture. Okay, and so just out of general curiosity, I know some people out there and students that I've got that are my high-level students are saying, well, what about zero-order and second-order reactions? Well, I'm going to go ahead and just go through these really quick. If this is concentration versus time, again, if it's zero-order, I know I have a straight line. If it's second, and this is, I'm going to go ahead and put zero-order up here, and then this is going to be my second order over here. I'm going to go ahead and pause the video, and I'm going to draw these graphs in, all right? Okay, and so here I'm back. I've got zero order, and I've already drawn in my kind of dash lines to get to my times here. But one thing I want you to notice here, notice the size of the half-life as I'm going from that first half-life to the second half-life. It's very apparent on my zero order graph. And one of the ways when we're looking at this integrated rate law data, this time versus concentration data, we can actually look at the graphical data of concentration versus time and almost begin to start looking at and defining the order there, just because we can look at the half-life. So notice, if it's zero order, right, the half-life time will decrease. As each successive half-life happens, it takes longer and longer for it to happen, all right? And so your half-life time for zero-order reactions in a concentration versus time graph will actually show a decrease. Now, for the other, what we see is actually the opposite of that, right? And so notice, and it's very, very apparent here, right? By the time I get to my first or my third half-life versus my first half-life, I can see that my half-life times are actually increasing for second-order reactions. And again, that's when I'm looking at this concentration versus time graph, and I didn't label those, but that's concentration versus time. I can start to look and say, all right, what's the half-life on these things approximately? In zero order, the half-life will show a decrease in time. first order is constant the whole way through, and then second order will actually show an increase, right? And so as long as we remember what we need to know, that first order is actually a constant half-life, then it makes sense 0 is less than 1, so those half-lives decrease, and second order is greater than 1, so those half-lives increase, right? And so just a little thing. These two things are not anything that you'll have to know, ladies and gentlemen, but again, it's kind of one of those things that helps point you in the right direction in your problem to identify what the order of the reactant is for this integrated rate law data. All right? Okay, so hopefully you got those two equations down. You understand how we're going to use them or have some inclination. We'll see some sample problems for those in class. If you have some other questions, make sure you get them down and come to tutorials. I'll see you there. Other than that, I'll see you in class.